This is it. This is the final lesson for Unit 3, Lesson 9 here. It's something called L'Hopital's rule, and it's actually one last method we've got for evaluating limits. And we couldn't see it until now, until we knew how to take derivatives. And it's actually useful for doing 6 slightly different types of limits, although only the first 2, these ones here, are going to be ones that could show up on the AP exam. These would be limits that when you look at the expression you're working with, it looks or it feels like a fraction that's 0 divided by a 0 or an infinity divided by an infinity. Now, there are a couple of, well, 4 other forms that we're going to take a look at in the notes here that are also nicely done with L'Hopital's rule, but they're not actually on the AP exam. But I'm still going to actually go over them in the notes here anyways. And you can take a look at them if you want. If you're going to skip these ones, this would be example 3, 4, 5, and 6, then do go to the very last page in the notes where we're just going to go over a couple more examples, again, actually of the first couple of forms to see how this game actually works. So the whole idea is that we're going to be playing around with what are called indeterminate forms. Basically algebra that doesn't seem to have decided what value it's actually going to be. And it could be something that's getting really small in the numerator and really small in the denominator, or the opposite, really big and really big. And L'Hopital's rule is really easy to execute. It says this: if you've got a limit of one function that's heading to 0 and another function that's heading to 0, and you're trying to do this fraction of one algebra over the other, then you can find the limit by instead doing the derivative of the top and the derivative of the bottom and trying again. And it also works if the two limits are infinity and infinity. And so we're going to try this out, and we're just going to go through these 6 different forms. And again, only form 1 and 2 are going to be on the AP exam, not 3, 4, 5, or 6, although you'll certainly see those in university. So we're going to cover them all here before we look at the last page, just to summarize some practice again. Okay, first example, let's do some 0 over 0. So if you were to just do a direct substitution with this limit, it doesn't work. The sign of 4 times 0 is 0, and the sign of 3 times 0 is 0. So I'm just going to be really just kind of casual with my language here and say this thing I'm using air quotes here too, right? Just keeping this really casual and say, hey, this thing feels like having a 0 divided by a 0, right? That's kind of the form that it looks like. And so how are we going to attack this? Well, we can use L'Hopital's rule. Now, on the AP exam, they're very clear about this, okay? There's something that you have to write down if you're going to do this. So I'm going to leave a little note here. You must, okay, absolutely must state this. You have to say, oh, I have looked at those limits of the top and the bottom, and I've noticed that they both go to 0. So we're trying to do a general limit on the whole fraction, but you have to say, look, here's what I'm noticing. The limit as x goes to 0 of just sine of 4x, that's heading to 0. And let me separately state this limit as x goes to 0 of 3x, that's also 0. That's required that you state that. You don't have to say, oh, now I'm going to use L'Hopital's rule, but you do have to mention that you've seen both of those limits separately going to 0. Then it is actually just this simple. We'll try doing a new limit where we take a derivative of the top and a derivative of the bottom and then begin again. So the derivative of the top would be the cosine of 4x, a little chain rule there, also kicking out a 4. All sitting on top of the derivative of the bottom. Okay, the derivative of the bottom would just be a plain old 3, and we'll do that same limit as x approaches the same value, which in this story happened to be a 0. All right, well that limit works perfectly fine if we do direct substitution. We end up with a 1 times a 4, so we end up with a 4 in the top and a 3 in the bottom, and that's our answer. So it's a really quick execution to do this L'Hopital's rule. Let's try it again with this other one over here on the other side, and we'll see something that can be a little bit interesting along the way. So it doesn't always go quite that smoothly. This one, again, I would say this is just very casual language. This thing feels like, if you try to do direct substitution, it feels like a 0 divided by a 0 when we let x approach that particular value, which just happens to be a 0. So I would have to do this. I would have to say, hey, look, here's what I've noticed. And if I don't write this out, my solution is not correct. I'd have to say, did you notice this numerator? And you just talk about the numerator. Hey, that's heading to 0. And hey, did you notice this denominator? 5x to the 4th plus 6x squared. As x approaches the same number there, that's heading to 0 too. All right, that's good enough to then let you begin using L'Hopital's rule. So we're going to do the same limit. X is going to approach that same value, happens to be 0. Won't always be 0, but that one's 0. And then we do a derivative of the top and a derivative of the bottom. And so the top would be 6x minus 1, and the bottom would be 20x cubed plus 12x. Now, in my little green brackets here, I'm just going to write down what it feels like if I try to do direct substitution. So this is just really casual here, right? Just casual language. The numerator, if I put 0 in for x, I end up with a -1. And the denominator, if I do a direct substitution, I get a 0. I have to stop at this point. It's no longer indeterminate. I can tell what the answer is going to be. This feels like a number divided by a number so small that it's it's heading to 0. The answer for this particular limit, I now conclusively know that it does not exist. Right? That would be my answer. It's getting so large that it doesn't have a value that it's heading towards. That's what happens when you get a 0 in the bottom and not a 0 in the top. Or if you wanted, you could say why it doesn't exist, that it's negative infinity, that it's just growing without bounds into the negatives. Okay, so sometimes that'll happen where you have a 0 in the bottom and then just a constant in the top. So that particular pair there in that example, that is the 0 divided by 0. L'Hopital's rule also works with ones that feel like infinity over infinity, and that's what this one does. When you look at the numerator, when we go to this x value of off to infinity, this thing, again, just casual language, this thing feels like, has this kind of form of a very, very big number in the top divided by a very, very big number in the bottom. And it's indeterminate. I don't know where this thing is heading towards. I would have to do this. If I'm going to do L'Hopital's rule, I'd have to say, hey, did you notice that when x approaches that interesting value, which just happens to be infinity, of this numerator, x squared plus 49x, that's infinity. And oh, did you also notice that when x heads to that value, when we look at e to the x, that's also heading off to infinity. Now it's fair to go ahead and do L'Hopital's rule. Let's try doing the derivative of the top and the bottom and then beginning again. So we'll still do the limit of x heading to the same x value, which happens to be infinity, but let's try a different limit out. Maybe we'll have more success with this. Okay, derivative of the top, that would be 2x plus 49. And then the derivative of the bottom, well, that would just be an e to the x again. So what happens when we try to do direct substitution here? Again, if I can just use my casual language in green here, what does this thing feel like? Well, it feels like we still have a problem. It still has this feeling of infinity divided by infinity. So it's still indeterminate. It's not like the last final example of example 1, where it's like, oh no, I can conclusively see it's getting out of control. I don't know where this is settling on. So this is going to happen with L'Hopital's rule questions, and my advice would be keep going. Just use the rule again. In fact, use it again and again. Okay, so apply the rule, apply L'Hopital again. Little caution here. You might need, don't let this scare you, but you might need to do it 3, 4, 5 times before you finally get an answer. And we're going to keep doing it as long as it has this feeling of infinity on infinity or 0 on 0. Now, if I am going to do L'Hopital's rule again, if I'm doing this on the AP exam, I would have to say, hey, doing a new limit here. Did you notice this? The limit of that numerator, 2x plus 49, it's heading to infinity. And oh, did you notice this limit? It's doing the same thing. The limit of e to the x. As x goes off to infinity, it's infinity. So then I do L'Hopital's rule again. I'm going to do the derivative of that top, that 2x plus 49. Well, that would just be a 2. And the derivative of the bottom, still an e to the x. And I'll do a limit as x goes to the value we're looking at. Happens to be infinity here. And so how does this thing feel? What's this thing doing here? Right? Very casual language, that's why I'm just throwing some air quotes on it. Yet this one feels like 2 sitting on top of infinity. 2 divided by a number that's so big, I can't imagine how big it is. I cannot do L'Hopital's rule again. I am only allowed to do L'Hopital's rule if it's infinity on infinity, or 0 on 0. Okay, so I have to stop here, and I have to make my call. 2 divided by a huge number. Okay, so kind of doing a direct substitution here. 2 on infinity, if I can say that. That is going to be 0. There's my answer. Okay, so again, a little caution. You must stop once it's no longer indeterminate. You can't keep doing L'Hopital's rule. You'll have to make a call for what you think the answer is when it is a form. Oh, where'd my pen go? Other than the ones that work. 0 on 0 or infinity on infinity. Okay, so we've done the 2 cases that can show up for the AP exam. Now for the next couple of pages, I'm going to show you some that you'll see in university but are not going to be on the AP exam. So you can skip the next couple of pages here and go right to the very last page if you want to. But if you want to see how this works, this is how you do it. So this one here has this feeling of 0 times infinity. It's like, well, what's that going to be? The 0 is trying to make the answer small, but the infinity is trying to make the answer big. And so as I do a limit when x gets really close to 0, and I'm doing 0 plus because I don't want negatives to go into the ln. That's the only reason why the plus is there. X to the 4th, well, that's heading towards 0. And ln of something that's really close to 0 is actually negative infinity. So I've got these 2 things fighting each other, and I don't know who's actually going to win. Well, here's how you deal with 0 multiplied by infinity. Change them until it either says 0 on top of 0 or infinity on top of infinity. Just move one of those things around. And I want to show you, like, there's kind of a good way and a bad way to do this particular one. So I'm actually going to split my page here. On the left side, I'll show you what does actually work pretty well. Now, I don't have a lot of room here to put in all those little AP justifications of, hey, did you see this limit? So I'm going to cheat a little bit and just save some space. So I'm doing a limit as x goes to 0 plus. And instead of writing it the way they've got it, how about I write this as the ln of 7x on the top, and then in the bottom, you're like, what do you mean in the bottom? Yeah, I'm going to move this x to the 4th to the bottom. And I can't just say x to the 4th. That's not the same thing. But I could say x to the negative 4. That's the exact same thing algebraically. And now I can look at it and say, hey, you know what? You put numbers in really close to 0. This thing feels now like an infinity, actually a minus infinity, divided by an infinity. So this is fair. I can now go and do L'Hopital's rule to this. It's back to my usual 2 cases. Now, again, I really should say, did you notice the limit of the numerator is heading to infinity? Did you notice the limit of the denominator is heading to infinity? So I'd have to make those statements, right in here, but I just don't have a lot of room. So I'm gonna be a little lazy and just, say, make sure you do it on the exam. But for now, I'm gonna sneak this in. So x is going to 0 plus. All right, doing a derivative of the top and of the bottom. So a derivative of the top, well, that would be 1 over 7x, a little chain rule, multiplied by 7. And then the derivative of the bottom would be minus 4x to the negative 5. Now the 7's reduce. I don't have to worry about them. They're gone. And what's left here? I've got this 1 over x, and then I have this x to the negative 5. Okay, if I just look at it like that, then this thing has this feeling of infinity divided by infinity again, right? So I'm not really too sure what to do with that. Let's try just cleaning this up. Maybe we can clean up the algebra a little bit. We won't even do another L'Hopital's here. Let's just see if we can rewrite this. Looks like there's a negative 4 down in the denominator for sure, but another way to clean these x's up, I could multiply top and bottom by an x to the 5th, and I would end up with x to the 4th all on top of negative 4. Okay, well, how does that feel when x heads towards 0, 0 positive? It's actually going to have a feeling of 0 divided by negative 4. It's not indeterminate anymore. I know what that answer is. That answer is 0. Okay, so that's my answer for that limit. So forget about the actual answer being 0. We had this 0 divided by, or 0 times infinity, and we just rewrote one of them, right? I chose to rewrite the 0 as being on top of infinity, and then I can go back to my usual plan. Had you tried to do it the other way, this is actually a bit of a disaster. So if you're like, oh, okay, well, how about I try to write this limit x goes to that x value that they're talking about, and how about we rewrite this fraction and clean that up a bit here. How about I leave the x to the 4th up in the top, but then move this ln to like 1 over itself down on the bottom? How about I write this as ln of 7x all to the negative 1? That now has a feeling that I know, right? First couple of examples were like this. In fact, that's example number 1. That's a 0 on 0. So it's fair to go for L'Hopital's rule. I really should spend a moment and say, did you see the top head to 0? Did you see the bottom head to 0? But I don't have a lot of room, so I'm going to jump right into this. All right, going for L'Hopital. Going to do a derivative of the top and a derivative of the bottom. And then we'll look at it again. Derivative of the top ends up being 4x cubed. That's pretty easy. The derivative of the bottom, kind of a chain rule. I got a negative 1. Got this blob here. Ln of 7x all to the negative 2. Then derivative of what's going on inside here, that would be a 1 over 7x multiplied by a 7. And again, I can reduce the 7s. That's pretty nice. Let's tidy this up a little bit because I can't see what's going on. So I'm just going to clean this up, see where this goes. Okay, the 7s went away. Got this 4x cubed. There's also this 1 over x. Let's multiply top and bottom by x. Going to move the negative as well. I would have negative 4 x to the 4th. And then down in the bottom, I would have ln of 7x all to the negative 2. This thing has a feeling now that is kind of like this. If you actually check out the numbers, it's a 0 all on top of like a negative infinity all to the negative 2, which is like a 0 as well. Basically, my point with this, it's getting worse. The ln didn't clean up and kind of go away like it did over here. So this was just not a good idea. So don't do it this way. You have to be open-minded and say, hey, that was getting worse. So instead of moving the ln to a reciprocal of a ln in the denominator, move the x to the 4th, do its reciprocal down in the denominator. And if you see it getting worse, just try the other option. Okay, option 4. What if you have an infinity minus an infinity? Well, you kind of need to know like which infinity is bigger than the other, right? And the feeling for this, if I can just put my feelings in little square brackets, 1 over x when x heads to 0, that is a very big number. And 1 over sine x when x heads to 0, also a very big number. I have no idea what that's going to look like. So I need to turn this into something that I recognize. And we can do it, and it works like this. We need one fraction. Okay, one fraction only, not two, where you have one minus another. So we have to go and get an LCD. Need that least common denominator, which here would be x multiplied by sine x. If I get everything up to that least common denominator, then things start working fairly well. So I'm going to do a limit as x heads to 0 plus, and I'm going to put this all into one fraction. Right, this first fraction, if I get to that least common denominator, would be, if I multiply both sides, top and bottom, by sine x, it would be sine x all on top of x sine x. And then minus, this one needs an x all on top of x sine x. Okay, well, now that they've got the same denominator, I could actually go and put them together. And I could say, okay, well, look, that's the same thing now as the limit as x heads to 0 plus of one fraction. The denominator is x sine x, and the top is sine x minus x. Now I can look at it and say, you know, when you let that limit go with x going to 0, that's going to have the feeling of, okay, sine of 0 is 0 and 0. That's a 0 in the top, and then 0 times 0, a 0 in the bottom. Okay, so that has a feeling that I recognize. This is totally fair to do L'Hopital's rule. I really should mention, I should take some time if I'm going to do this on the AP exam, and I should one at a time mention these limits. You know, I should say, hey, did you notice that this heads to 0? And then another little statement, did you notice that heads to 0? I just don't have a lot of room here, so I'm going to skip that step and say, all right, let's do L'Hopital. So I'm going to do a limit. X heads towards that same value, 0 plus, and now it's time to do a derivative of the top and a derivative of the bottom and see what this looks like. So the derivative of the top would be cos x minus a 1. And then the derivative of the bottom, it's a product rule. So derivative of x is 1 times the sine x left alone, and then minus, I should say not minus, I should say plus x times the derivative of sine x, which would be cos x. Okay, there. I just took a derivative of the top and a derivative of the bottom. That is how L'Hopital's rule works. And then you go and try a little direct substitution out and see how it feels. And the feeling for this one is in the top. If I put a 0 in, I get 1 minus 1. I have a 0. And then down here I'd have 0 plus 0. Okay. Hey, it's still indeterminate. So keep going. Right? As long as it's 0 on 0 or infinity on infinity, you have to keep going. If it was the AP exam, I would take the numerator and say, did you see that? Head to 0. And then take the denominator and say, did you see that? Limit out to 0. Then do L'Hopital's rule. But I just don't have a lot of room. So I'm going to jump right into it. Okay. See if this gets any better. So the derivative of the top would be minus sine x. And then the bottom. The derivative of the bottom would be a cosine of x. And oh, here comes a product rule. Derivative of x is 1, so plus cosine x. And then we would have plus, leave the x, and then the derivative of the cos. So an x sine x, there should be a negative in there. I'm going to go back, use my eraser, and say, yeah, picked up a negative. Okay, so what does that feel like if I try doing direct substitution here? And well, here it actually works. Come on, Pat. There we go. If I go and think about doing a direct substitution, I get a 0 in the top, and then I get a 1 plus a 1 minus a 0. So I actually have a 2 in the bottom. Can't do L'Hopital's rule anymore. It's time to make a decision and say, hey, here's the answer. The answer to this question is going to be 0, right? If you have that 0 in the top and then a nice constant down there in the bottom. So if it's infinity minus an infinity, we want to get one fraction. and get a common denominator to get there. Now, the next two are definitely tougher. Like hands down, they're not as easy, but they are doable. We're going to try to do 0 to the 0 and see what that does. It is a tricky question to try to do this. Normally if you have 0 as a base, you'd expect 0 for an answer. But if you have 0 in the exponent, you'd expect 1 for the answer. So I don't know, where's this thing actually heading towards? This is a hard limit to do. And so what I want to do is I want to take this expression here, this x to the x. That's pretty tough to deal with. It's intimidating me. I'm not too sure how to work with it. And I'm just going to give it a new name, right? Because this sort of bothers me. I'm like, geez, that's a really hard thing to work with. How about I go and just call that Q? I'm going to call it Q for question, right? So here's their question. They're saying, could you do the limit of x to the x? And then we're gonna actually try a different question out that'll be easier, and then we'll come back to their question. But their question is, can you do the limit of this thing called Q? Here's our general plan with this. And it's not easy, but it's doable. It's actually really hard to try to do the limit on this thing called Q. To try to figure out what that is, that's challenging. But what's easier, okay, I'm going to say easy, but it's easier, is to do the limit of not Q, but how about the ln of Q? Let's figure out what the logarithm of their question would do. Then we can go and figure out what theirs is like. So I know that Q is equal to x to the x. Let's take that right there and let's do the natural logarithm of both sides. If I do a logarithm over here on the right, I can pull that x down. So let's try this here. I've got ln of Q would be the ln of x to the x. But that could be rewritten in a slightly nicer way as x times the ln of x. So I don't really want that option. I'm going to take the x times ln x. So let's do the easier limit. Okay, and then we'll talk about doing the hard limit after that. So this is slightly easier. It's not even their question, but we're going to give it a try. How about we do the limit as x goes to 0 plus, because that's what they want, of the ln of Q. Let's do the limit as x goes to 0 plus of x times the ln of x. All right, well, how would that feel if I was to put 0 in? We've actually done one like this in an earlier example, very similar to this. This is going to feel like a 0 multiplied by a negative infinity. Ah, okay, I know what to do. You have to take one of those and move it to the other side of the fraction bar so it looks like a fraction. And what I learned was that you probably don't want to put the logarithm down on the bottom there with a -1 on it. So let's move the x. Let's rewrite this question. Okay, we're going to do the limit as x goes to 0 plus. Let's turn this into a fraction. I'm going to leave the ln where it is. And then x, I'm going to write that down on the bottom as being a 1 over x. Or if it's okay with you, how about a x to the -1? So now it doesn't feel like 0 times infinity anymore. Now when I try to do a little direct substitution, if I make an attempt at that, I get a negative infinity on top of an infinity. That's kind of classic L'Hopital's form. So I'm going to, if it was an AP exam, I'd say, hey, the limit of ln is infinity, and the limit of x to the -1 is infinity. Then I'd be ready to try to do L'Hopital's rule, where I'm going to take a derivative, top and bottom, and then try again. So we'll do a limit as x heads towards 0 plus. And we'll just do a derivative of the top and a derivative of the bottom. So a derivative of the top would be 1 over x, And a derivative of the bottom would be negative x to the negative 2. Okay, well, I can actually clean that up a little bit. Let me just move this a little bit. I need some space. I could say, hey, let's just clean the algebra up so I can see it. What have we really got here? Well, up in the top, if I multiply everything by an x squared, I'm going to have a negative x all sitting on top of a 1. That's totally clear to me what this thing is going to do. You know, the feeling right now when I do a direct substitution is a 0 on top of a 1. I know the answer. That answer is 0. But here's the catch. I did not do their question. I did the logarithm of their question, and I found out what it was doing. So we have to do one last little Math 12 maneuver here. And I'm going to just put a little note in here. So now, at this point, we know that the ln of their question heads to 0. It limits to 0. Right? That's what this is saying. It's kind of like saying we know that the ln of q is going to 0. Here comes the last question, though. Well, what about q? What about their question? What's it doing? So we're just going to have to rearrange this. We're going to take that logarithm and write it in exponential form. So a natural logarithm, of course, that's base e. And the natural logarithm of their question seems to be heading towards 0. Okay, well, let's just invert that. Let's rewrite that in the other form. Let's write it exponentially. The 0 is apparently the exponent on the e in order to get to q. So e to the 0 is equal to q. Ah, okay, I can see that. That's just a Math 12 deal here. It looks like if the ln of q is heading to 0, then q, their question, must be limiting to 1. So the answer to this limit is that it's 1. So it's a little bit interesting with that one. We kind of saw that ln coming because we had a variable x up in the exponent, and we can use the logarithm to pull it down. And we did a trick where we didn't actually even do their question. We did the logarithm of their question instead. And we're going to see that that happens also on this sixth and final form. What if you have 1 to the infinity? If you have 1 for a base, you'd expect the answer just to be a 1. But if you have an infinite exponent, you'd expect that maybe the answer would really, really grow. I'm looking at this thing here, and if I put in infinity for x, if I do 3 divided by infinity, that's 0. Sine of 0 is 0. That's 1 plus 0. Okay, so that's a 1. And yeah, that's like a 1 to the x, which is going, oh yeah, it's exactly what they've said. It takes a little while to get there, but this thing looks like a 1 to the infinity. So I'm going to look at their question and say, really? That's pretty awful looking. You know, all this stuff that they've got right here. Ugh, right? That whole limit that we were trying to do. Thanks, but no thanks. So I'm just going to say, yeah, that's their question. Really don't want to do that. How about we go and just give that a name, right? We'll call it Q. So we've got Q is going to equal 1 plus the sine of 3 over x all to the x. It's really hard. Like, I don't even know how to do it. It's really hard to try to do the limit. They want x to go to infinity. It's hard to do the limit of q. So let's not. Let's do this one. It'll actually be easier. Maybe not easy, but it'll be easier. Let's do the limit. X can go to infinity, but let's not do it for q. Let's do it on the ln of q. Because then we'll be able to pull that x down from up there in the numerator. Okay, so taking this expression here, this purple expression, let's just do the logarithm of both sides. We're going to have the ln of q is equal to, all right, going to do a logarithm over here, but I know why I'm doing it. I'm doing it so I can pull the x down. So let's jump right into that logarithm rule. We'll save ourselves a little bit of time. There. Just exercise the log rule right off the start. I want to try to do the limit of that stuff and see what it does. So here goes. I'm going to do this easy limit, right? Here, maybe I'll put it in green because it's a little bit easier to do. So what is the limit as x heads to infinity for this blue stuff right here, this x multiplied by the ln of 1 plus the sine of 3 over x. Well, what's the feeling for that? I've got an infinity here multiplied by, now this ln of 1 plus sine of that, that's like the ln of 1. Well, that's actually a 0. Okay, so we have that 0 times infinity again. We want to write that as either an infinity on infinity or a 0 on 0. We got to turn this into a fraction in order for this easier limit to be doable. Okay, I'm going to move the x. And what we've seen is it's probably better to leave that logarithm up in the denominator. Up in the numerator. So I have ln of 1 plus the sine of 3 over x. Let's just leave that there. Now the x can go down on the bottom if we write it as x to the negative 1. And if you just ask yourself, well, how does that feel? This particular fraction has a feeling of 0 divided by 0. So we really should, if I had more room on the paper, say, hey, check out the upper limit, check out the lower limit. Notice that they're both 0. Then I can go and do L'Hopital's rule. So here it comes, L'Hopital's rule. Let's do this again, but we'll take a derivative of the top and a derivative of the bottom and hope like crazy that it actually gets a little bit better. So a derivative of the top, ugh, that is awful looking because you've got this crazy blob here. Whatever, we can work with it. We're going to have 1 over that blob. So we'll have 1 over 1 plus the sine of 3 on top of x. That gets multiplied by, now the derivative of what's inside. Well, the derivative of 1 is 0. And then the derivative of the sine with this weird little argument there, that'll be cosine of that weird fraction, that weird angle. Then I have to multiply by the derivative of that. If it's okay with you, I'm going to think of this as being 3x to the negative 1. So when I do a derivative, that's going to be negative 3x to the negative 2. It's just easier than doing a quotient rule inside there. And the derivative of the bottom, negative x to the negative 2. Yeesh. We got to tidy this up. Oh, hey, look, this isn't too bad. We've actually got a x to the negative 2, x to the negative 2. So that goes away. I'm going to rewrite this, kind of hoping to be able to see this a little bit better. Still hoping I can do this easy limit, or easier limit. Okay, with a full rewrite, how does this look? There is a 3 hanging around, so that can go up there. The negatives cancel there as well. There is a cosine of 3 over x, kind of an interesting angle. And then that is going to go down in this denominator here. We're going to have a 1 plus the sine of 3 over x. Okay, so how does this feel if you put infinity in? 3 over infinity is 0. Cos of 0 is a 1. 1 times 3 is a 3. Oh, this might work. In the bottom, 3 over infinity is 0. Sine of 0 is 0. Add 1 is 1. Oh, okay, this is definitely determinate. I know how this is going to go. This is going to head towards 3. But that's not their question. That's the logarithm of their question. So now I need to say, okay, look, here was the easy thing. I found that the ln of their question, it headed towards 3. But they're like, yeah, that's very nice. What does 3 do? Or sorry, what does q do? Well, of course, logarithms are base e. So let's just go and take this and rewrite it in exponential form. We'll just spin it around in exponential form. Going back to their hard question, I guess, we would say e to the 3 is equal to q. Ah, okay. I know the answer. It looks like this thing, their hard question, it's limiting out to e cubed. That's my answer. The answer is e cubed. So that 6th example is one of the 4 that you won't see on the AP exams. But at the last page here, back to some that could show up on the AP exam. Let's see what we would do with these. Doing a limit as x goes to pi. You know, x could go to anything, right? And then we'll do a little direct substitution here to see what this feels like. So if I try putting a pi in, cos of pi is a -1, plus sine of 2 pi, that's a 0, plus a 1. Oh, okay, we have a 0 in the top, and then in the bottom, pi squared minus pi squared, oh, a 0. Okay, it's indeterminate. It's just the easiest form that we worked with, 0 divided by 0. I know for the last few examples I was lazy and sloppy. Let's fix that. You know, if you're on the AP exam, okay, again, you need to write this out. You'd have to say, did you notice the limit of the top, just the top? Did you notice how that was heading to 0? And then you say, oh yeah, and by the way, did you notice this limit? And you have to mention these separately as 2 separate limits. Let this thing finish saving here. There we go. Minus pi squared. That's also 0. Those have to be stated. You can't just do that thing that I have there in green. That was just me being casual. And now we're going to go and do L'Hopital's rule. So it'll still be a limit as x goes to pi, because that's what the limit was. And now we'll try doing derivatives of the top and of the bottom, and then see what happens. Well, derivative of cosine is a minus sine. And then here, got a little blob going on there. We're going to have a cos of 2x, and then a little 2 gets kicked out from the chain rule, and the derivative of 1 is going to be nothing. Down at the bottom, derivative is just 2x. Okay, so how does that feel if you go and put in pi for x? And the answer is it's settling down on a number. In the top, if you put pi in, sine of pi, that's 0. Cos of 2 pi, that's going to be a 1 times a 2. Okay, we have a 2 in the top. And then in the bottom, a 2 pi. Nothing indeterminate about that at all. This is totally determined. This is going to be 1 over pi. That would be my answer for that one. Again, I was sloppy on the last few examples, and I didn't write in what I have here in red. It does have to go there. And now I'm going to get sloppy again for number 8, and you're going to see why. All right, first attempt at doing the limit as x goes to 0. You end up with 0 minus 0 on top of 0 minus 0. So you have nothing on nothing. Okay, it's indeterminate. So you would state, in like I have in red over here, oh yeah, the limit of the top is 0. The limit of the bottom is 0. You'd have to do that. I just don't have enough room here for this one. Write small. Okay, the limit as x goes to 0. Let's try again, but let's go and do L'Hopital's rule. So we'll do a derivative in the top and a derivative in the bottom. The top, after a derivative, becomes 2 cos x. And the bottom, sorry, continuing on, didn't finish this, minus 2 cos of 2x. Right, that 2 gets kicked out from the chain rule. The bottom becomes 1 minus cos x. So you try that out. You say, okay, what does that do when we go and put 0 in? And the answer is, it's still indeterminate. It's actually a 0 divided by 0 again. So you would restate, like I've done in red on the left, the limit of the top is 0, the limit of the bottom is 0, and then you would go and reapply L'Hopital's rule. So we're going to hit it again. See how this looks. Okay, derivative of the top would be -2 sine x. And then we're going to have another 2 get kicked out. We're going to get a +4 now, sine of 2x. And then in the bottom, we would have just a sine x. So you try doing direct substitution. Well, guess what? You get 0 divided by 0 again. Just keep throwing L'Hopital's rule at it. So we're going to do L'Hopital's rule again, and you keep doing it until one of those zeros gives up. Maybe they both do, but we're going to keep going until something happens. So we do a derivative in the top, and we get -2 cosine of x. And then another 2 comes out from the chain rule, and we're going to get +8 cosine of 2x. Down in the denominator, we do a derivative there, and we get cosine of x. And so you try putting 0 in for x. And when we do that, with a little direct substitution attempt, we end up getting a -2 plus an 8. We get a 6 in the top. Okay, it's finally broke. The 6 has turned into something, or the 0 has turned into a 6. And then down in the bottom, we get a 1. Definitely determined. My answer for this one would be a 6. So a couple of lessons here with that one. Don't be afraid to keep throwing L'Hopital's rule at it. Once, twice, 3 times. And don't be lazy like me and make sure you write those red steps out every single time. Final example for the chapter. Just a question that I found. It's kind of neat. And it's one of these, hey, what do you think is true here? First of all, let's graph this function. It's a function by piece. 2 chunks that are both lines with slope of 2, but different y-intercepts. The first line has got a y-intercept of -2, and we're allowed to graph that until we get right up near 3. And as you limit this out near 3, 6 minus 2, we're going to be kind of limiting out near 4, but with an open circle. Okay, and a y-intercept of -2. So that looks like that. Then it skips, has a little discontinuity, and we're going to have this 2x minus 4, same slope, but it's going to have a different y-intercept. It's actually a lower y-intercept. That'll kick the whole thing down a couple of steps, and that'll look kind of like that. Okay, what's happening here? First of all, just want to point this out, that if somebody did ask you, hey, what is f at 3? Well, you would look here on that branch. 2 times 3 is 6, minus 4 is a 2, right? And that's the solid point that's in right there. Okay, so which of these is true? Got a couple of limits from either side, and then this overall derivative at 3 is equal to 2. So they're saying the slope there is 2. Well, we're going to do this kind of backwards. First thing I'm going to do is say that's wrong. Okay, that's not true, and here's why. There is no tangent line at x is equal to 3. And this is saying, oh yeah, there'd be a tangent line and the slope is 2. But no, that's not true. So there is no tangent at x is equal to 3. Right? How would you draw in a tangent line? Like where does it go? Does it? I don't know. Like it just doesn't make sense. It's not even continuous. There's no way it could be differentiable and have a tangent line. So 3 is out. Now, this is a bit of a sneaky question because you might be thinking that these limits, that are here are kind of like saying this. And so I'm going to just scribble this down and say, well, could we rewrite these like this and say, hey, let's look at the limit of the derivative as x gets really close to 3, but on the low side. And let's go and take a look at the derivative when x gets really close to 3, but from the high side. And you might think, yeah, that's what those things are saying. It's like doing Newton's limit, but just on either the low or the high side of that 3. But it's not totally true. This one is actually the same thing. This is saying, if I can go up here, it says use 3 as one of your points, and then use a place a little farther down the road, 3 plus h. So 3 would be right where that solid blue dot is, and 3 plus h would be like some point right there. And then you bring the pink point close to x equals 3, and you would find that, yeah, you're getting this slope of 2. And so that one is a go, right? It's like, yep, that's a fair statement. And you might be thinking, well, that's what this other one's doing. It's trying to do the derivative, but it's just trying to do it, like right here. But it's actually not. If you look at the instruction, it's using 3 for one of the x values, and then 3 back a little bit. So in terms of the points that you'd be trying to do this grade 10 slope with, one of those points would be here, but the other point would be this blue dot down there. And as you bring that pink dot closer and closer to x is equal to 3, that red line doesn't settle on any nice slope, and it certainly doesn't settle on 2. So this one is a no, and it's not quite the same thing as what's sitting here. So just be careful, right? They're not really the same. So if I was doing this test, I would say let's go with this. Let's go with just B. And that technical little example brings us to the end of this fairly long chapter on taking derivatives without using any limits.